Hello everyone. The audio didn't record from the review session, so I'm gonna re-record everything we did there for the people that couldn't make it. But this is the resource I made for studying. It's available on Piazza if you want to follow along. But it's based off of the practice exam, but I added some more stuff on there. Try and get some more knowledge. Anyway, we're just gonna start from the beginning. So we're gonna start with our conversions. So before we start conversions, we want to think of how base number systems work. So if you didn't already know, the numbers we use on a day-to-day basis are actually in base 10. Why is that? If we have number 123, right, we have a tens place and a hundreds place and a ones place. Right, so if we have a hundreds place, tens place, and ones place, we can break down 123 as 1 times 100 for the hundreds place, 2 times 10 for the tens place, and then 3 times 1 to the tens for the ones place, sorry. And it's we think of it as the tens place and the hundreds place and the ones place, but in formality, this is actually the 10 to the second place. This is the 10 to the first place. And this is the 10 to the 0th place. So this is how the base 10 number system works. So for each digit in our base 10 number, let's denote this specifically as base 10 like this. For each digit, it corresponds to one of these things in the sum, where it increases by a power of 10, from 10 to the 0, 10 to the 1, 10 to the 2. What defines it as base 10? See how these exponents all have base 10. And if you also think about it, our number system for each digit has 10 unique symbols, 0 to 9, which sums up to 10 unique symbols. So binary is just the same thing but base 2, and hexadecimal is the same thing but base 16. Let's give a hexadecimal example. So let's say we have number 21 in hexadecimal. So in our base 10 number system, this would just be 20 plus 1, right? But in base 16, this would be 2 times 16 to the first plus 1 times 16 to the 0. So similar process, except the base is now 16. And we could also have instances where you have numbers looking like this, F3 or something. Because hexadecimal, because it's base 16, we need to have 16 unique ways to identify digits. That's 0 through 9, and then A, B, C, D, E, F. Oops, let me, still recording? Yeah. Which correspond to 10, 11, 12, 13, 14, 15, 16 unique symbols for a digit. And obviously binary, same sort of deal, except with only 2 symbols, 0 and 1, which is why it's base 2. So that's how a base and number system works. So knowing that and understanding that, I feel like it makes it easier to convert from one to the other. So if we look at 1011, 0101, and we want to convert it to decimal, well, let's do this. Since we know that it's a base 2 number, let's start by taking this piece by piece. So 1 times 2 to the 0 plus 0 times 2 to the 1, right? I'm just taking each digit one by one. 1 times 2 to the 2, and so on and so forth. And then this is just going to equal some value, which will actually be in base 10, because we're converting this number into its actual value, which we can recognize. Here's a shortcut for doing this. List out your powers of 2. 16, 32, 64 for every digit or every bit in our bit string. So we have 8, so we wrote out, oh, sorry, missing 1. We wrote out 8 powers of 2. And then just write the bit string right under it. And then wherever is a 1, that's the base 10 value it corresponds to. Just add them up. You get 128 plus 32 plus 16 plus 4 plus 1. And you can compute that yourself. That'll be the decimal form. And binary to hex is actually super easy, because if you think about it, binary is just kind of like the long form of hexadecimal. Or I guess a better way to say it is hexadecimal is a shorter way to represent binary. Because if you think about it, if you have 4 bits, so let's just say these are 4 bits, we have 2 possibilities for each of them. So therefore we have 2 to the 4 unique combinations of these 4 bits, indicating that 4 bits can represent 16 unique things, right? Because we have 16 unique ways of writing zeros and ones in 4 spaces. Remember how we said there was 16 hexits? So actually, each of these 4 bits corresponds to exactly 1 hexit. So this is why if you're like printing out a memory address or something, you'll always see it in hexadecimal. In reality, it's in binary, but hexadecimal just makes it a little more readable and more compact. So how do you convert this? So you want to, again, check it each chunk of 4 at a time. And let's just check this chunk. So let's convert it to base 10. So 1, 1, 0, 1. And then this will correspond to 1, 2, 4, 8. So 8 plus 2 plus 1 is going to equal 11. So that's 11 base 10. Remember, each digit in our hexadecimal corresponds from 0 to F, which is 0 to 15. So we just got to find what 11 corresponds to, which we see here is just B. So this first bit string of 4 is going to be B. And I'll leave you guys to find the second one. Hex to binary, really simple, again, because hexadecimal is literally just a short form of binary. So we want to convert B7 to binary. Let's consider B. So let's take this 1 hexit. A hexit, by the way, is just 1 digit in hexadecimal at a time. So we know B corresponds to 11. So how do we represent 11 in binary? So this is an exercise in converting from a value to binary. So let's just take the process we took before. So we list out the powers of 2. And let's just work in reverse. Let's, instead of pre-writing the bit string, we need to find the bit string that corresponds to 11. So if you think about it, the way to do this is you write 1, 0, 1, 1. Because if you take 8 plus 2 plus 1, that'll equal 11. So B directly corresponds to 4-bit string 1, 0, 1, 1. And again, I'll leave you to solve 7. Convert B7 to base 10. Here you need to think of the base number system. Remember we had like 123, and it was like 1 times 10 to the 2 plus 2 times 10 to the 1 plus 3 times 10 to the 0. It's literally the same exact thing, except we're changing up our base. So we're taking B times 16 to the 1 plus 7 times 16 to the 0, right? That's how the base number system works. You take each digit, and it corresponds to one of these. And B is just how you represent the value 11. So this is just 11 times 16 to the 1 plus 7 times 16 to the 0. And that'll evaluate to the base 10 value. Convert 23 to binary. Again, let's take that process we used earlier to convert from a value to binary. Write out our powers of 2. 8, 16. And you won't have to write out 32. Why? Because 32 is greater than 23. If we try to give a 1 to this 32, we immediately overshoot the value we're trying to represent. So you only need to include up to 16. And then how do we create 23 from these? This would be 1, 0, 1, 1, 1. Because 16 plus 4 plus 2 plus 1 exactly equals 23. So 23 to binary is exactly 1, 0, 1, 1, 1. And finally, 23 to hexadecimal. We already have the binary representation. Let's use that. 1. So remember, every group of 4 bits corresponds to 1 hexit. So we have a group of 4 here, but you might ask, We can't do it here because we only have 1 bit left. We don't have a group of 4. Well, in binary, if you think about it, if you just add leading zeros, it won't alter the value at all, right? Because we're not adding anything else. We're just putting leading zeros. So we can just add 3 zeros there, and boom, there's a chunk of 4. It's 1. So then, if you want to convert it to hexadecimal, see what values each chunk represents. So this represents 1, because this is just 0, 0, 0, 1. That's just going to represent 1, so that's hex at 1. And this side will be 4 plus 2 plus 1, which is 7. So therefore, 23 in hexadecimal is just 17. All right, here's some questions on deciding whether things are stored in the stack or the heap. So the stack is where the main program happens, right? That's where your stack frames are for the methods you call in the main method. That's where, most importantly, stack variables are, which are usually primarily primitive types. What I mean by primitive, these are things like integer, double, lowercase boolean, things like that. Things that only are there to store a value. Now the heap, think of it like extra storage for your program. It's just kind of like out in the back, it's just extra storage. This is where you're going to store things like reference types, like objects, arrays, things like that. Anyway, let's just work through the questions. In x equals 5, obviously that's on the stack. It's a primitive type. And then double is also primitive, so that's on the stack. Now we have 2 strings here, and they're declared in different ways. I want you guys to know that these 2 are synonymous ways of declaring a string. This way is actually just a shorthand of doing this way. But at the end of the day, both of these are reference types, because a string is not a primitive type. It is an object, meaning that Java has defined somewhere there's like a class string, like in the java.util or some package somewhere. It's a string with different methods like 2 lowercase or, I don't know, length, stuff like that. So here's a way to know in your head if something is a heap or a reference type. If you can take the variable and there's a way to do like dot length or something, that means this variable is a part of the class and it's an instantiated object and it lives on the heap. And here's an array of strings. What I want you guys to know is that array contents always live in the heap. So this will be on the heap. What we'll cover later though, if you might not already know, arrays contain something in the stack and in the heap. But for the purpose of this question, it's asking whether the following are stored in the stack and heap. It's always referring to the actual elements themselves. And for arrays in Java, the contents of the arrays are always going to be on the heap. Here is a Boolean on, but it looks a little different. Typically, we want to see Boolean on equals true, just like that. But we have Boolean on equals new Boolean true. So I'll tell you guys now, this is on the heap. Maybe the new gives it away because it's an instantiated object. But that doesn't make sense because we could have declared just like a regular Boolean, which is just a primitive type. What is this weird one? Well, every primitive type in Java has an elevated object type. For example, there's a double class, capital D. There's an integer class. And the reason why you want to declare like an elevated version of these variables is that these variables have additional functionality which might be useful. Maybe like on.toString or something like that. So yeah, every primitive type can be upgraded or declared with its wrapper class, is what it's technically called. So just keep that in mind. Another array immediately, its contents are always on the heap. Here we have an instance where we're instantiating a new object. This is where you want to be careful. Don't always just differentiate between stack and heap by the uppercase, because though uppercase is a good convention to use for declaring a class or an object, it's not necessarily required or enforced by Java. So this, even though it's all lowercase, this is technically still in the heap because it's a reference type. We're instantiating a new class, so be careful with that. And here's a tricky one. You might think this is immediately on the stack because it's a primitive type, but notice this. It's declared as private. So this is declared as an instance variable somewhere. Say we have class dog, capital D, dog, right? And then we give it a instance variable, private int age. So even though it's an integer, age is an instance variable. It's a value that describes the object. It's actually part of the object. So because this variable is part of the object, it's what defines the object. And objects are reference types that live on the heap. This implies that X will be on the heap as it's part of an object. So you guys want to be careful with that. Primitive types are not always on the stack. They can be on the heap if they're declared as instance variables of objects, because then they become part of an object. All right, here, this is to illustrate the strengths of arrays and how elements are found within them. So we're given an array of length 5, starting at address 100, and we want to state the exact memory address where the following elements are located. So let's detail this by drawing out the array. So it starts at 100, we know that. A primitive integer is always going to be 4 bytes. Each address corresponds to pointing to 1 byte, so it's 1 to 1 byte for each address. So we know the first element will be from address 100 to 103. Why? 100, 101, 101, 102, 103. This is 4 addresses to hold 4 bytes for the first integer. So this is going to be I equals 0, or the first element. And then remember, things in an array are always contingent, or right next to each other. So the next element will start at the next address right next to it, and this will be from 104 to 107. And then the chain just keeps continuing because they all have to be right next to each other, right? Equals 2, and so on and so forth. So this is how things are stored in an array. An array should have all the same byte length or byte size of the data type. In this case, we have this holding because every element in the array is 4 bytes. So they're going to be evenly spaced, and they're all right next to each other. That's what defines an array, and the reason why this needs to hold is because it allows us to retrieve an element instantly. So let's just start with A of 0. A of 0 is obviously returning it's obviously referring to where the first element is. We already said the first element is going to be where the array starts, obviously. So this is going to be at address 100. Now what about A of 3? Do you see what we have here? We have kind of a pattern. Look at this. I equals 0, 100, 104, 1, 108, 2, and so on and so forth. You see that at A of 3, it should be at 112. Because, judging by this pattern, the address at A of n, arbitrary n, is just going to equal the starting address. In this case, it's 100, plus I, times the size of element. In this case, it's 4. Do you see that? Because I have 1 at index 1, it's at 104. That is exactly 100. Let me do this in a different color. 100 plus 1 times 4. And now I equals 2, it's at 108. It's exactly 100 plus 2 times 4. So it follows that A of 3 should be at 100 plus 3 times 4, which equals exactly 112. So this is why arrays are so powerful, because there's this direct formula to get any element at the ith index. Moving on, these questions are designed to detail how different kinds of arrays are stored in the stack and the heap. It's kind of a quirk of the language. But we're given this, first of all, we're given this integer array. There's primitive integers. And we want to create a diagram of the stack and the heap, assuming that a pointer is 8 bytes. So here we go. So we have the heap. We have the stack. So remember what I said the contents of the array will always be in the heap. So we're going to assume that the actual 1, 2, 3, and 4 are going to live somewhere in the heap. Let's just say it's at address like 300. Okay, don't think of like addresses too literally. This is just arbitrary. There's no like preset delimitation between which addresses are stacked in the heap. That's something the program just arbitrarily decides and does in the background. We're just saying 300 for convenience sake. But let's say the array starts at 300. Okay? Now we want to see exactly how many addresses will this array span. Well, let's look at where the last element is, right? So the last element is going to be at defined array. It's going to be 0, 1, 2, 3. So it's going to be a defined array 3. Notice this is primitive integer. So using the formula, we have the starting address plus 3 times 4. So the last element will start exactly at 312. This is an integer, so it takes up exactly 4 bytes, meaning it will span from 312 to 315. So knowing that the last element spans until 315, it follows that the array itself must end exactly at 315. So the array spans from 300 to 315, totaling 16 total bytes, which makes sense, right? Because we have 4 integers, each of size 4 bytes. So this is where the array 1, 2, 3, 4 lives. So this is really nice, right? Because this is a nice integer array. We know exactly how big an integer is, which is 4 bytes. So we can just store them all right next to each other really easily. But this is in the heap, right? Our program is happening in the stack. That's where the program is happening. So we need a way to kind of reference or have like a pointer to exactly where this whole array situation is living. So let's just say we have pointer here. So defined array. This will equal at 300. So first of all, in Java, the variable itself, when you're like looking at it from your program, consider it like a pointer, right? It contains in the stack, exactly 1 pointer, which is going to be 8 bytes. So I guess there you go. That's where the pointer lives. So it's pointing at 300. Let's just say it lives from 100 to 107. So I got off track, sorry, but this is pointing, what I'm saying is this is pointing to 300, and the pointer variable itself is living in addresses 100 to 107 on the stack. So we're pointing only to where this array begins, right? Because with the formula, we know how big the data type is. All we got to know is just where it starts, and then we can find any element within it. We don't need to have pointers to every single element in the array. That'd just be redundant. So what's stored in the stack is just a singular pointer to where the beginning of this array begins. And this pointer itself, consider a pointer like its own data type. It's its own data type, which is specifically going to store byte addresses to some other point in memory. So that's what's stored in the stack. So the array itself is stored in the heap with a reference to where it begins in the stack so that the programmer, can interact with it. Right? That makes sense, but now here's where it gets a little different, because now instead of a nice primitive type like an integer where we know exactly how big it's going to be no matter what, we have a string, right? So how big is a string? We have no idea. We can have a string which is 1 character, or we can have a string which is like 1,000 characters. It's kind of like a variable sizing. It doesn't have one defined size. So that's going to pose an issue if we try to store it like one after the other in the array, right? Because all of the things in the array have to be the same size for this formula to work. Does that make sense? Like, because each block is evenly spaced, we know exactly how far to look to find the exact element. So we can't define a specific size on the string. How do we deal with this? Here's how Java deals with this. So instead of all of the strings being one next to each other in some kind of array in the heap, the strings are going to live independently. So maybe let's just say at 317 in the heap, there exists the first string in the array. And then maybe like at 433, the second string lives there. And then maybe at like 573, I don't know, string 3 lives there. And so on and so forth. What I'm saying is that unlike before, where all of the elements can just live happily with each other in a block, in a nice array with an integer, we have no choice but to kind of just like toss wherever is available for the strings, because we have no idea how big they're going to get. If we try to put them all in a row, it's not going to work. So we need them to have their own spaces to begin with. And that way, if we like add stuff or remove stuff from the strings, Java will know how to resize them, maybe remove them. But it'll be easy because they're not all in a row. They're just kind of living out on their own. So you might ask, where isn't this an array? Like, where are we getting benefits of the array? The actual array data structure. So again, the elements of the array still live on the heap. They always live on the heap. But the array data structure is actually going to live in the stack. So in the stack, we have an array of pointers. 43. What was this? I don't even know what number I wrote here. What was this, like 523? At 523. And then so on and so forth until we get all 10 elements. So in the stack, we still have an array, and we can still instantly access whatever element we want in the array. And it works because all the pointers are all the same size. Pointers are always the same size because it's just like a data type. So we still get the benefits of an array, but it's just like a little different because the array is just going to contain references to where the string lives. So it requires another step for us to jump to the heap once we get the element we want and then actually access the string. But that's how it works. So just remember, for primitive types, it's super easy because the whole heap can live contingently in the heap, or the whole array, sorry, can live contingently in the heap. And for reference types, they're kind of spread out, and what ties them together is an array in the stack which stores the references. That's where the array lives. Okay, here is a linked list. I'm not going to do the first part because I actually ripped this from the practices again. If you want to practice like constructing a linked list, I do the problem exactly. I do the problem itself on the practice exam and check your answer. I feel like it's pretty straightforward. What I do want to cover, though, is how deletions work. So we want to illustrate how element 15 would be removed from the linked list first. Okay. So we want this to happen. We want this to be gone. So then our linked list will just be 1 to 9 instead of what we had before, 1, 15, 9. We want to remove this, right? So in Java, there's no way to just like tell something to remove itself from memory. I do not believe. We can't just tell the second node, can't just call some method delete on the second node, which instantly removes it from memory. And that would lead to issues, because if we just did that and we thought we deleted it, well, this is pointing to 750, and if it's pointing there and it goes there and there's nothing there, well, then you just messed up the entire linked list, because then how is it going to get to 800, right? Here's what we do. So we look at the element before. So let me box it up so it looks a little nicer. So this is node 1, and this is node 2, and this is node 3. The way we can delete node 2 is, instead of node 1 saying the next node is node 2, why don't we just say the next node will actually just be the third node, which lives at 800. So we essentially deleted 2 just by skipping over the one that we don't want and just directly going to the next one. So in reality, what's going to happen is our linked list is just going to look like 1 to 9. So we deleted 15, right? That's how that works. you don't explicitly delete things from linked lists. You just change the pointer. And here's another case. How would you remove tail element 9? Same kind of deal. So you look at the one before, which is 2. I'll go D&D. Sorry. And then we're looking at element number 2, which is the second to last one. We don't want element 2 to jump to element 3 because that's the one we're trying to remove. So what if instead of element 2 pointing to 800, what if we just make it point to null, right? What if we just tell the program, just end at node 2? Well, then effectively we're just going to have a linked list that just goes from 1 to 15 and then ends there. So we removed the tail element. So gist of what I'm saying is to remove things from linked lists, you just alter the pointers. Now we're going to get into some time complexity. So here's like all of the ones on all of the data structures that you should be knowing for this first midterm. And we're just going to go through the best, worst, and average time complexity of the following. So let's start with the worst time complexity of searching a sorted linked list. So a sorted linked list, you might think sorted, so use a binary search. Well, actually, a binary search on a linked list wouldn't work. Because a binary search requires you to start at the middle and then kind of like chop your way down, divide and conquer the rest of the elements. But a linked list is very limited in that you can't just like jump to the middle element instantly, right? A linked list has to have it to where you have to start at the beginning and then you have to work your way up to where you want to go. So even if you wanted to start at the middle, you'd have to start at the beginning and then work your way up to the middle. By the time you get to the middle, you've done 1/2 AND operations, which is just an O of N operation. So binary search is not a possible thing on a sorted linked list. The best thing you can do is just directly search the elements one by one, one at a time. So O of N. Best case scenario, the element is the first thing in the list, right? So no matter how, what the hell? No matter how big your linked list is, if the element you're trying to find is just the first one, then it doesn't matter how big it is, you just use a constant amount of operations to find that first one. So that's O of 1, right? The size of the linked list has nothing to do if it's just the first one. You don't even look at the rest of the elements. And then average, like you'd think the average would be like maybe the elements in the middle of the list. So you do 1/2 N operations maybe. That's just going to be O of N. And you want to drop all coefficients, that's why it's O of N. You want to think of this very heuristically, very generally. Don't pigeonhole yourself into like a certain case. Unsorted linked list, it's actually going to be the same thing, right? Because searching through elements, you just have to go one by one, same thing. The linked list being sorted doesn't really change anything. So the best case is O of 1. Still, that would just be the first element is the one that you're trying to find. Average is O of N. Same thing. That's what's limiting about a linked list data structure. Unlike an array, where you have the luxury of just jumping to wherever you want and getting the element there, you have to start at the beginning and work your way up. However, if you guys remember, the reason why you'd want to use the linked list is it's because it's more efficient with memory. Because in array, you have to predefine a whole block of memory, and maybe you only use like this much, but you have that much empty space allocated just to doing nothing. Linked list uses this memory efficiently, right? Because it's just a chain of stuff. So that's like the trade-off you make. Anyway, deletion from a linked list. Guys, remember, for deletion, you assume that the element you're trying to delete has already been found. So the searching for this element is not included. It's just a deletion. So deletion from a linked list is really easy. Remember that thing we did with the pointers? No matter what, it's just going to be like one of those pointer changes, which is just O of 1, constant operations. No extra work. All you got to do is change that one pointer around, and you're done. All right? Now, searching a sorted array. This is where binary search happens. So O of log n. So because we can instantly get to the middle and conduct our binary search algorithm, we can actually perform binary search with O of log n times. So this is what's good about a sorted array. You get the luxury of performing the nice binary search algorithm. It's O of log n. And if you're wondering what O of log n means, just think about it like every iteration you do, you have the amount of things that you have to look at. So maybe like if you start with n equals 32, after iteration 1, maybe you'd only have 16 things left to look at. After iteration 2, you'd have 8 things left to look at, 4, 2, and then 1 thing left to look at, and then you'll solve it. That's why O of log n is much faster than O of n or maybe O of n squared. And best case, again, it's to search. Think about if you're searching through something and the first element that you look at is actually the element you want to find. That's really nice because then you just return that. No matter how big or small the array is, if you get super lucky and that first element is the one you're looking for, you don't need to look through the rest of the elements, right? You just found it. So that's O of 1. And average is still O of log n. Now, searching an unsorted array, you don't get the luxury of doing binary search. If you know how binary search works, the only reason why it works is because the array is pre-sorted. If it's unsorted, you have no pattern or variation in the elements to go off of. Your best bet is to just start at the beginning and just start searching one by one. There's no better way to search an unsorted array. So that's O of n, because you're just searching through things one by one, right? Best, same story. First element is what you're looking for, and average is O of n. Now, deletion from an unsorted array in a sorted array you need to think about. So let's consider an example. Unsorted array, 3, 7, 5, 2, 6, or something, I don't know. So this is just an array with numbers in it. No particular order, no patterns or nothing you have to uphold. If we wanted to remove 5, okay, we removed 5. Now there's this hole in the array. You can't have holes in arrays, right? Because all the elements have to be contingent. Well, luckily for an unsorted array, it's really easy to fill that hole, and you can do it in constant time, actually. Because you just take the last element in the array, and you just fill up space, right? And the last element's gone. So if you just take the last element in the array and you just fill up the space, that's constant time, right? Because you always know where the last element is, and it's really straightforward to move it. No matter how big the array is, it's constant time, because it just takes a few operations to get that last element and move it to where the empty spot is. So this is going to still be O of 1. Best time complexity, you can't get better than O of 1, so it's still O of 1. And on average, still O of 1. Now, for a sorted array, you need to be careful, because unlike the unsorted array, you don't have the luxury of just moving the last element to the empty space. Why? Well, let's consider a sorted array, just simple 1, 2, 3, 4, 5. So if we wanted to delete 2, okay, 2 is deleted, and now we have a gap. We can't have a gap in an array. If we tried to take 5 and move it in, we now violate our sorted array constraint, right? We need the array to be sorted, because whenever you delete something, we're assuming that the array will remain sorted. We have 1, 5, 3, 4. That does not work, right? What you have to do, the only thing you can do here is after you move it, you have to move each element one by one down one spot. So boom, boom, boom. So because you have to do that for every element after the element you deleted, think of the worst case, right? So say you have an array of like n elements. It's just like, I don't know, arbitrary array of n elements. And you remove the first one. First element. Well, you got to move this one, and then this one, and then this one, and do that approximately n times. So if you're doing that approximately n times, you're doing about O of n operation. Okay, but then for best case, think about this. Oops. What'd I do? Think about this. What about the lucky case where you have array like 1, 2, 3, 4, and we just remove the tail element? Well, if we just remove the tail element, there's not going to be any spaces left for us to fill. We don't have to move anything down. So in this lucky case, it's just going to be O of 1, because you just delete it and you don't have to move anything down. And then on average, it's going to be O of n, because if you remove like a middle element or something, it's going to be 1/2 n operations Again, just O of n. Think of it very generally. And here's a case where we have multiple operations in sequence. So here's an operation where we search for an element in a sorted array and then delete it. So we already figured this out. Searching for an element in a sorted array, on average, will take O of log n. And then deleting it will take O of 1. Now, if you're just asked straight up for the big O, it's assumed that you're trying to find the worst case complexity, worst case time complexity. So let's look at the worst case time complexities for the search and the deletion. So the search is O of log n, and the deletion is search for a sorted array and deleting it. So we have an O of log n operation followed by an O of n operation. So if you think about it, if we're first doing an O of log n operation and an O of n, what's going to happen is that this whole operation is actually just going to be O of n. Because this O of n operation is basically just going to like overpower this O of log n, right? It's not going to be O of n log n, because O of n log n is something completely different. This would be like searching for an element in a sorted array n times and then deleting it, which is not what we're doing. We're just doing one thing, which takes O of log n, and then another thing right after that, which is O of n, and then we're done. So the whole thing would be O of n. It's bounded by O of n, because O of n outpaces O of log n, right? And here's another example. Searching it for an element in a sorted array, and then deleting the last element in the array. So the search is O of log n. But then, if we delete something, if we delete the last element in the array, we know that to be an O of 1. So this will just be an O of log n operation. Now these two problems will look at code and then analyze their time complexities. But you want to be careful with these. So this first one, we say a developer calls a method do stuff on their array exactly 40 elements. And we're asked, what was the time complexity of the algorithm the developer utilized? So looking at this, we have this outer for loop. It's going to be running a.length or n times. So immediately this outer for loop is implying so far O of n. And then we have an inner for loop. So for every iteration of this outer loop, we're running this inner for loop. And you might instantly think nested for loop, that should be O of n squared, right? But you got to be careful, because this inner for loop is not running also n times. It's just running 40 straight times. 40 is a constant. No matter how big n is, or the length of our array, it's always going to run 40 times, whether A is an array of 1,000,000 elements, 10 elements, whatever. So this whole algorithm is going to be O of n. Now this could be tricky, because we said they call this on their array of exactly 40 elements. So because we're running this 40 times, isn't that n? Well, you got to be careful, because you got to look at the algorithm as a whole. Even though the developer called this on their array of 40 elements, that doesn't make this whole algorithm O of n squared. Because if we used any other size array, like 1,000,000 or billion size array, then that wouldn't hold, because this is still always going to be running 40 times. So that's what I'm saying. You got to look at these time complexity problems very heuristically and look at them from a very general case. And here we have a recursive method. This is a typo. This is supposed to say do recursive stuff. But we have a basic recursive function. If you look at it, you might instantly think O of n, because this is just decrementing by 1. So we're going to be doing like a number of calls on itself until it hits less than or equal to 0. But technically, this would actually be O of a. So n refers to the size of the collection that you're inputting. This is why this first algorithm is O of n, because we inputted a list with n elements. So n is just kind of like a proxy or a variable that represents the size of the collection that we input. The reason why we see O of n so much is because a lot of algorithms need to be implemented on collections. But it doesn't always have to be n. Here, we're going to be running this algorithm approximately a times. So this is O of a. Though it operates like though it is in linear time, you would technically need to denote this as O of a. So I just included this question to show that big O is not necessarily required to have n. It can be bounded by other variables as well. All right, that's it.